The verdict should not be decided by an administrator. It should be decided by scientists working on the data from 3i Atlas. And one of the shortfalls of this particular press conference was that no scientists that analyzed the NASA data were included. It was officials from NASA. And moreover, what the message the officials conveyed was that it's a boring object. It's an object similar to the comets we're familiar with, except it came from a different environment. That is not the case with 3i Atlas. In fact, it has 12 anomalies that were not even discussed during the press conference.
A week after NASA released its HiRISE image of 3i Atlas, most observers shrugged and scrolled on. The frame was underwhelming, a dim, ambiguous smear adrift in a black field with none of the high-definition clarity the HiRISE camera is famous for. The public explanation was equally unexciting. Difficult target, low lighting, fast motion, a convenient cluster of technical caveats that made it sound as though the Mars Reconnaissance orbiter had simply caught the interstellar visitor at a bad moment. But Earth exists. A private research collective team known for forensic-level data digging didn't look away. Instead of accepting the surface-level narrative, they opened the raw data package NASA published to the planetary data system, dug through the directory structure, read the headers, inspected the configuration files, and scrutinized every line that revealed what the spacecraft actually recorded. What they found didn't match the public story, not even close. The deeper they went, the more the official version unraveled. The low-resolution frame released to the public was not the only data the instrument had captured. The metadata revealed that HiRISE had captured far more than the single 8-bit grayscale frame NASA released. It showed the camera firing in full capacity, recording high-resolution 14-bit data across multiple channels: red, NIR, and blue-green. These additional bands, which would have revealed heat signatures, compositional clues, and structural detail, never appeared in the public archive. Instead, only one heavily altered strip was released, while the directory contained placeholders and missing file markers indicating that the other exposures once existed. The contrast between the expected multi-band dataset and the lone degraded output was stark, suggesting that the publicly released image represented only a fraction of what HiRISE actually captured. The headers and timestamps made this discrepancy even clearer. They confirmed that all 3 channels fired successfully, with no error flags, memory gaps, or failed exposures, meaning the instrument worked exactly as intended. Yet only one channel made it to publication. Downsampling 14-bit data to 8-bit erased the subtle gradients that revealed jets, thermal patterns, reflectance differences, and any faint structural features, flattening everything into a uniform smear. Because NASA's planetary data system normally follows strict archival standards, the disappearance of entire channels while their operational footprints remained was highly unusual. Mechanically, the metadata documents a complete multi-band capture followed by a deliberate single-band release, contradicting the narrative that the target was simply too dim to image. The metadata discrepancy would have been unsettling enough on its own, but it becomes even more provocative when placed against the backdrop of the object's behavior. If HiRISE had captured a routine comet, there would be no reason for a complex multi-band dataset to be compressed, stripped down, or selectively released. But 3i Atlas has not behaved like a routine comet. From the moment its signal entered astronomical records, the object has exhibited a series of anomalies that have challenged researchers, confused expectations, and disrupted every model that scientists normally use to classify interstellar visitors. In this context, the missing bands and the degraded imagery don't just look like technical shortcuts, they look like gaps in a story that is already filled with irregularities. If the imaging data appears curated, the object's behavior appears even more so. An improbable sequence of traits and coincidences that no one has been able to fully explain.
One of the earliest and most striking anomalies involves the behavior of the jets emerging from the object's surface. Under normal comet physics, a rotating body emits jets that appear to sweep or smear over time, creating arcs or curved plumes in long exposure images. This is because the source vents rotate with the nucleus. Yet for 3i Atlas, the jets remain oriented in a fixed direction, almost pinned in space, as if the object were not rotating at all. But rotational measurements suggest the object completes a spin roughly every 16 hours. If that rate is accurate, the jets should be smeared across the visible coma in every observation. observation. Instead, they remain astonishingly straight, coherent, and stable, violating the rotational smearing expected for a body emitting dust and gas while spinning. The only way to reconcile these observations is to assume the vents are aligned with such precision or constrained by such an unusual mechanism that their emissions remain stable regardless of rotation. That is not how natural comet jets behave. The jet orientation also displays a second, closely related anomaly. Not only are the jets not smeared, they seem to be aligned with suspicious precision toward the sun. Comet jets sometimes point roughly sunward because sublimation is driven by sunlight, but 3I Atlas appears to produce jets that maintain an unnaturally consistent alignment, with an angular stability far greater than statistical norms for known comets. Researchers have noted that the vent locations would need to be positioned with almost engineered precision for this to occur, firing in a way that keeps the outgassing directed even as the object rotates. This creates an odd situation. The jets act as if the body either isn't rotating, or is rotating in a way synchronized to maintain jet direction, or is controlled by an internal structure or pattern inconsistent with random vent formation. Any of these interpretations land outside standard cometary dynamics. Then there is the matter of the orbit itself. Interstellar objects follow almost any inclination imaginable. They come from all directions because they are not part of the solar system's architecture. Yet 3I Atlas, despite being retrograde, is aligned within roughly 5 degrees of the plane in which the planets orbit the Sun. This specific alignment is statistically improbable for a random interstellar body. It implies either a bias in the object's ejection trajectory from its origin system, unlikely without special conditions, or some form of steering, modulation, or prior gravitational influence that pushed it onto an unusually planar trajectory. Researchers have tried to calculate the odds of such a precise alignment occurring without outside influences, and while the estimates vary, all fall at the low end of probability. The orbit's geometry is the kind that raises eyebrows not because it's impossible, but because it's too precise to ignore.
The strangeness doesn't stop there. After passing unnervingly close to Mars in October 2025, 3I Atlas continued on a path that leads to another remarkable rendezvous. On March 16, 2026, it will pass near Jupiter at a distance so close to the planet's Hill sphere, the region where Jupiter's gravity dominates, that the encounter borders on suspiciously exact. Objects do not normally thread the needle of multi-planet close approaches without gravitational nudges, yet 3I Atlas appears to be doing exactly that. If non-gravitational acceleration, outgassing, were random, it would push the trajectory off course, not refine it into a near encounter with the solar system's largest planet. The consistency and directionality of the object's course have led some researchers to propose that the trajectory is being tuned, whether by internal physics or by something less mundane. The Jupiter pass in 2026 has even been described as a potential opportunity for the object to shed smaller fragments into stable Jovian orbits, using gravitational capture mechanisms that are complex but theoretically predictable. Its outgassing behavior deepens the mystery further. Interstellar comets typically exhibit erratic, chaotic outgassing because their surfaces are volatile and unfamiliar to solar radiation. But 3I Atlas shows outgassing that is both stronger and more consistent than expected, even though the jet orientations remain stable, which contradicts basic thermodynamic models. Non-gravitational acceleration driven by outgassing has been detected, yet the pattern does not match typical rotational dependence. Instead, the acceleration appears disproportionately aligned with the jet directions, as though the jets are not only stable but also producing thrust-like behavior. This duality, stable orientation plus significant acceleration, creates a paradox that researchers have struggled to resolve. In natural comets, stronger outgassing usually means more chaotic jet motion. In this case, it has produced the opposite. Chemical and compositional anomalies have also surfaced. Reports indicate that certain emission lines, particularly those associated with specific metals or unusual volatile ratios, do not conform to the expected profile of known interstellar material. Some observations suggest stronger than expected nickel emission without corresponding iron signs, a ratio that is chemically peculiar in natural bodies. Other spectroscopic hints point to possible asymmetries in the coma that could signal structured emission or compositional layering. None of these findings alone would overturn the natural interpretation, but together they form a pattern of low probability behaviors. Atypical jets, atypical composition, atypical orientation, atypical trajectory. Each one is an outlier, but the stacking of outliers creates a more troubling question.
Considering all of this, the unusual handling of the HiRISE data begins to look less like a coincidence and more like part of a larger pattern of irregularities surrounding this object. If NASA perceived the object as ordinary, the release of a full multi-band dataset, complete with color, thermal signatures, and structural details, would have been routine. But when the object itself displays characteristics that scientists struggle to model or explain, the decision to release only the lowest information version of the data seems less like an oversight and more like a protective measure, whether the reason was to prevent public misunderstanding, avoid sensationalism, or delay interpretation until more analysis could be done. The outcome is the same: a significant observational event captured by one of humanity's sharpest orbital cameras was distilled into a single flattened smear. At this point, the anomalies demand a deeper inquiry. The fixed jet orientation alone challenges existing comet physics. The improbable planar orbit further strains natural explanations. The coordinated close approaches to Mars and Jupiter border on an astronomical choreography. The stable yet powerful outgassing suggests an emission process with an internal regularity, not random sublimation. Even the rotational paradox, jets unaffected by spinning, implies a mechanism or geometry that has no precedent in known comet behavior. Some researchers have suggested exotic natural interpretations. Perhaps the nucleus is elongated in a way that aligns vents along a single axis. Perhaps the rotation is unusual or slower than estimated. Perhaps the composition includes volatiles that emit in tightly focused, non-diffusing jets. While these explanations are possible, their improbability grows with every new anomaly added to the list. The speculation spectrum widens when the Jupiter encounter is introduced. If 3I Atlas were an object designed, whether by nature or by something else, to drop fragments or conduct surveys near large gravitational bodies, then its precise approach to Jupiter begins to look intentional. Jupiter's Hill sphere acts as a gravitational gateway where even small objects can be captured into temporary orbits. It is a region where artificial objects could theoretically release probes that would remain bound. While such scenarios stray into the territory of advanced engineering, the mechanics are not impossible, just highly improbable for a natural interstellar traveler. Yet improbability is the recurring theme with 3I Atlas. This pattern leads to the same fork in interpretation every time. Either the object is a natural outlier, somehow representing a rare but valid statistical tale of cosmic behavior, or it is something else entirely, an object whose characteristics align more with design than chance. Avi Loeb and other researchers emphasize that extraordinary claims require extraordinary evidence, and that no single anomaly should push anyone to a non-natural conclusion. But a dozen anomalies, a dozen deviations from expected behavior, each one requiring its own special explanation, at some point the rational mind begins to question whether randomness can produce so many coordinated irregularities.